In this video, I'm gonna introduce another type of the optimization solution. One is called the linear program. In the linear program, it's kind of constrained problem. So you solve the minimization. You solve the minimization with constraints. So the goal is to find the parameters in your model that minimize for example the linear functions of your W dot product such that with some constraints such that A W less and equals to B. Okay, so here usually this A is a n by D matrix, W is a D by 1 vector, and B is n by 1 vector. Okay, so what's this mean? This I'll give you some geometric interpretation here. This C represents a vector in the W plane, right? So if we have the W1, W2, this means a direction in the X in the W1, W2 space. Okay, and you can think each linear inequality here is a line. For example, you can think this the first equation is a line, and below okay. And the second equation is this one, third equation is this one, fourth equation, third equation. So, and we have this feasible region. So this is called the feasible region. Okay, and we are looking for the point that which is we are looking for a point that is furthest in the C direction. Okay, for example, this C is the direction here. So among all the points inside this feasible region, so this is our optimum point, so W star. Okay, actually this feasible region in the linear program has a name called the set of W points satisfy all constraints. Is a convex polygon. So polytop is a high dimension polygon. So here we have 2 dimension, it's a polygon, but in the higher dimension is polytype. This is our feasible region. F. Okay, so this is For example, this is our f. And the optimum point is a point in f that is furthest in the direction c. In the direction c. Okay, for example, in this example, this is our solution for this linear program, satisfy all the constraints. The optimum achieves equality with some constraints called active constraints. For example, in this case, we have two constraint boundary conditions that this optimum point cross two. So this two condition is called active constraint. So, for example, in the support vector machine, the active constraint corresponding to the training points that touch or violate the maximum boundary margins. Those points are known as the support vector. Okay, so in other words, in our decision boundary problem, so we have the hard decision. We have the hard margin support vector. We have some points. So those points right on the margins, or if in the soft margin support vector machine, those points with the slacks. With the slacks means those points are on the active constraints. So those points are called support vectors. Therefore, the classification algorithm we introduced in last class is called a support vector machine. Okay. So the point is we want to find a feasible point. But if the problem should be linear separable, right? So, for example, here maybe I give you one example. In our linear classifier, feasible point omega alpha gives a linear classifier. So we are looking for, so the hard margin decision boundary, we are looking for find omega and alpha. So you can think this is our W in our linear programming problems, such that yi has the same sign as xi omega plus alpha greater than or equals to 1 for all I. Okay, so for this problem, we are looking for a points that is satisfy all these constraints, right? Satisfy all these constraints. But not this feasible region is only non-empty only if the data is not is linearly separable. Okay, and the most famous algorithm for linear programming is through the simplex algorithm. Just to introduce you some names. These are all implemented in our Python package now. Simplex algorithm. Okay, the author is by the famous mathematician George Danzig. The simplex algorithm is indisputably one of the most important and useful algorithms. It works along the edges of the feasible regions. For example, maybe if you have starting point is here, you go ahead and search the closest vertex, and you search along the next vertex, until you find the optimal one. And the linear programming is a very different from the unconstrained optimization. It has much more combinatory flavors. If you know which constraints would be the active constraints once you found the solution, it will be easy. But usually this algorithms is computational expensive. So for linear programming algorithm tend to have a very discrete solutions, and the computer science feeling to them like a graph algorithms, where the unconstrained optimization algorithm tend to have continuous numerical mathematical feelings. Okay, so that's a linear programming. And the last one we talk about is called quadratic programming, which is exactly what we used to search for the soft margin support vector machine. So quadratic program. So we have so the only difference is objective function in the linear programming is a linear function, but in the quadratic program, the optimization target function is a convex quadratic form. So objective function is quadratic convex function, and with same constraint with linear, again we still need to have the linear constraints. So the goal for quadratic program is to find the minimizer omega that minimize Fw equals to W transpose. Q is a matrix. Q is a D by D matrix. So this is 1 by D, and this is D by 1. So this will be a scalar plus C transpose W. So this is called quadratic form. So this is called quadratic form. And subject to the same linear constraints, AW less than or equals to B. Okay, so here maybe I can give you one more example. So the idea is very similar to the linear programming, but now the object function is always quadratic and convex. So this is one example. This is the our soft margin support vector machine. Remember, in soft the objective function we want to minimize is we want to find minimize to minimize. We want to find minimize the omega square, which is equals to minimize of the, if we have two dimension, it's w1 square plus w2 square. Okay, so w1 plus w2 square in the feature is a circle, right? Is a circle. So now we just give different all kinds of the constraints. In the two dimension, each constraint corresponding to a line. Okay, for example, if we have some features, we have some constraints like this one, has like this one. Okay, so probably the solution will be in the contour line. We want to find a point that tangent to a circle, So this it will be our optimum solution. Okay, so this is just one example where we apply. We already know this. In the lab, you already applied this to solve the quadratic, to solve the soft margin support vector machines. Okay, so this technique is called quadratic program. And usually this Q is positive definite. If, for example, for our case, you can think f w equals to w1 square plus w2 square. This is just equals to w1, w2 multiply a matrix, diagonal matrix, w1, w2. Okay, so this is our Q matrix. If this Q matrix is positive definite, so our quadratic form always have the local, only one local minimum. Okay. Usually we want to solve the problem is positive definite. So what's positive definite mean? So means all the eigenvalues are non-negative. What if the Q is not a positive definite? Then the optimization function in this case is not convex. Minimum always may not be unique. So that problem is a little bit hard. And all the algorithms for the quadratic programming is like so in the Python it's called simplex like algorithm to solve such problems. Or there is also called the sequential optimization, minimum optimization. Okay, and I think in sklearn package. Such problem can be solved by, it's called the linear support vector. Okay, so this is the command to solve this quadratic optimization problem. Okay, I think that's all for today. Thank you.